Every light in the city dies at once. Hospitals switch to backup. Water pressure starts falling. Traffic signals vanish. And the power plant across the river is dark too. Except this station is different. Its hydro units can wake without outside grid power. In this city's restoration zone, it is the only available machine that can make the first spark. You are the restoration lead. Close the right breakers, and one generator becomes a living grid. Close the wrong one, and the tiny system collapses back to zero. So what do you turn on first? This city is fictional, the problem is not. The lines are assumed intact enough to use, trained crews and private radios are available, and protected systems have a one-day scenario clock. Real restoration plans supply the rules. You supply the decisions. Your first problem is annoying. Power plants consume electricity before they produce it. Controls, pumps, switchgear, cooling, fuel equipment, and communications all need what the dead grid no longer provides. Most large generators are stranded. The hydro station cheats the paradox with small on-site emergency systems. They wake the controls, move the intake gates, and let falling water spin Unit 1. A lamp flickers on. The city does not notice. You now control a grid with one generator and essentially one customer, the plant itself. That sounds small because it is. Generation and demand must match every second. Add too much load, and frequency falls until protection trips. There is no city switch. The Blackout map is a maze of silent substations, open breakers, uncertain lines, and feeders that combine thousands of devices. Before sending power anywhere, operators have to prove a safe path exists. Some telemetry is gone, so a field crew drives to the first substation and radios back the readings. The switching order was planned before the blackout. This is not improvisation with bigger buttons. It is choreography performed in the dark. Your instinct is immediate: power the hospital. The restoration plan points somewhere less satisfying, the station's second hydro unit. That machine is not a patient, a water pump, or a traffic light. It is reserve. If Unit 1 trips while it is alone, every minute of progress disappears. Unit 2 gives the island redundancy and more room to absorb sudden demand. You choose reserve. The second turbine begins to turn. It feels cold, but the choice is not hospital versus machine. It is fragile power now versus enough stable power to keep the hospital on later. The clock keeps moving while the plant powers itself again. Now electricity can manufacture more electricity. Crews energize a planned transmission path toward a much larger gas turbine. The hydro station is not meant to power the whole city. It is acting like a starter motor for the next engine. But a turbine cannot burn electricity. The gas pipeline must still have pressure, its valves must work, and the operator must be reachable. A radio call confirms the fictional scenario's next assumption: fuel is available. Cranking power reaches the gas turbine. Pumps and controls wake. The shaft accelerates, synchronizes with your tiny island, and begins generating. The hydro station has done something far more useful than lighting homes. It has started another power plant. You finally have meaningful capacity. You still cannot energize everything. The board lists substations, gas support, water treatment, communications, a hospital district, traffic corridors, and residential feeders. Every item is urgent to somebody. This is not a clean moral ranking. Some loads keep people alive directly. Others unlock the ability to serve all the rest. Substation controls and gas support go first because losing generation would erase every later promise. Next, operators pick up a carefully sized water and control block. Pumps begin turning, reservoirs stop draining, and the new demand gives the generators useful stabilizing load. The city receives a service before it receives a skyline. Then the hospital feeder closes. Emergency systems begin transferring back to grid power. One bright district appears on the map. Most homes remain black, but the restoration now protects people instead of merely preparing to. The obvious next win is emotional. Light an entire neighborhood. Thousands of dark windows would switch on together. The feeder looks small enough on the plan. You approve the pickup. During the outage, thermostats kept asking for cooling, compressors stopped mid-cycle, pumps lost pressure, and motors cooled down. When power returns, many devices restart together. In some systems, the first surge can reach up to 10 times normal for a few seconds. The breaker closes. Demand leaps. Your frequency needle drops as generator governors pour in more water and fuel. They respond fast. The load arrives faster. The tiny grid begins moving toward its protection limits. You order the feeder shed. The neighborhood goes dark again just before the generators trip. It looks like failure from the street. From the control room, it is the decision that prevents the entire island from dying. That is the trick television blackouts hide. A city does not return in one heroic reveal. Restoration happens in electrical bites small enough for the living island to swallow. The new strategy is slower and much better. Split the feeder, pick up one block, wait for the restart surge to settle, raise generation, check voltage and frequency, then repeat. Lights return as scattered islands. Water pumps here, a hospital district there, communications near the river, traffic control along one corridor. The result is less cinematic than a skyline and far more believable. All of this depends on people outside your room. Crews verify equipment, plant operators report limits, dispatchers track the balance, and radio teams carry instructions when normal communications fail. You lead a system, not a joystick. Then a message arrives. A neighboring region has built its own stable island. Connecting it would add generation, reserve, and new routes into your city. It would also create the most delicate move of the night. The two grids cannot simply touch. Operators must align three things: frequency, voltage, and phase angle, the exact position of their alternating waves. It is a three-lock door with a very large breaker for a handle. A badly timed close can trigger violent electrical forces, protection trips, or instability. So both sides adjust generation and voltage while dispatchers watch the phase gap shrink. The breaker stays open until every lock agrees. Frequency matches, voltage matches, the waves slide into phase. Coordination approval arrives. The tie breaker closes and two fragile islands become one stronger grid. More routes and more reserve are suddenly available. The city is not fully restored. Many homes are dark, damaged equipment remains isolated, and every new block still needs checking. But essential services are stable, more generation is online, and the recovery can now accelerate. So, can one power plant restart a dead city? Not by powering the city directly. It can create the first stable electricity that wakes other generators, control systems, transmission paths, and carefully selected loads. The last useful plant is not the city's engine. It is the starter motor that wakes the engine. Its power matters because it can make more power possible. And the real superpower was never one turbine. It was the prepared path, the tested plan, the crews, radios, fuel, reserve, and constant balance that turned one spinning machine into a coordinated recovery. Beyond the city, another region remains black. Its generator is ready, its fuel is waiting, and its only cranking path crosses a failed substation. Power is useless when there is nowhere safe for it to go.